Thanks so much for the opportunity to speak. I'm going to try to share my screen, see if this works.
Have with us Professor Susan COPPERSMITH. She has done a great, important work in many areas in condensed matter physics, quantum information, and many other topics. And she'll be talking today about exciting results in quantum stochastic resonance. Please go ahead. Thanks.
Yeah, okay, thanks. Again, thanks so much for the opportunity to talk with you. And I'm going to talk to you about quantum dynamics. I know Franco because I've worked on some problems in quantum computing, but I decided to talk about this because this is a little topic where it's relevant to some quantum technologies, but the ideas are quite general. So I wanted to talk about stochastic resonance because it turns out it's broadly applicable. I'll tell you about that. And also it is relevant to nanotechnology and the single spin dynamics. And so actually is useful for quantum technologies that people are developing today. So I did want to say that I am going to show you experiments. They were all done in the group of Sebastian Loth, who is at the University of Stuttgart. And this picture is, these pictures are from Professor Loth's webpage. And this one on the left is not an actual picture of an STM tip putting electrons through individual atoms, but that is what the experiment is, but this is just an artist's rendition of what's going on in the experiment. And anyway, but I'm really grateful to them for the opportunity to try to understand their experiments and to tell you and to sort of we think we understand and we think we'll be able to use the phenomenon I'm talking about to be able to control these spins at the individual level. Okay, so so again, the talk is on quantum stochastic resonance. And so first I'm going to talk to you about stochastic resonance, which was originally developed in the early 80s as an explanation of the periodicity of the Earth's ice ages. So I'll tell you a little bit about that. It's, I think, a really interesting story. And and a lot of work was done based on it. And I'll try to give you some sense of the scope of the area. The way I got involved in the field was sort of accidentally. I started thinking about the question of, can you see something like stochastic resonance in quantum systems? And this was something that actually I worked on quite a long time ago. This work was done with Rick Philofstadt, who was a graduate student at the time. And what we found was that yes, in principle, in theory, yes, quantum systems can also show stochastic resonance. And but the experiments were not done at that time. I'll try to give you some sense of why that is. And it was very exciting to me to see the tremendous developments in nanotechnology that made it so that now we can. The experiments I'm going to show you, I think, are really convincing and extremely well controlled. And again, what's actually being measured are individual spin transitions of individual iron atoms sitting on a substrate. And so this work was published last year, and I think really demonstrates that this kind of phenomenon occurs not just in the Earth's ice ages, but also on the single atom scale. So as promised, I'm going to tell you first what stochastic resonance is. And it's a little bit historical because, again, I really love the story of how I love the story of how it got started because of just the generalities of the ideas of theoretical physics, I think, could be really inspiring. And this is one of these cases where the story of the model originally, I think, is very inspiring. So these are the original papers, and I did want to point out that Parisi, who is one of the authors of these papers, won the Nobel Prize last year. Now, Parisi did a lot of things besides stochastic resonance. He absolutely, deserves this Nobel Prize. But stochastic resonance was listed as one of his major accomplishments, not his biggest, but a major accomplishment. Okay, so let me tell you how the original presentation. Okay, so what this graph is actually a Fourier, it's a Fourier transform of a measurement of oxygen isotope content in fossil plankton. Okay, and what this is a proxy for temperature. Right, so it's like really hard to go back. This is, as you see, this goes back 1 million years, and there aren't thermometers going back 1 million years. So basically, scientists use proxies like this, where basically the fraction of oxygen 18 to oxygen 16 varies a little bit, and it depends on what the Earth's temperature is, just because of the amount of plant cover, for instance. Okay, so they took the time series and they Fourier transformed it, and they plotted the power, and you can see there's actually quite a strong peak in this time series of the Earth's temperature. And this is basically the origin for thinking there is essentially an approximate periodicity in the Earth's ice ages. All right, and what Benzi et al. Did was they were trying to come up with an explanation for this phenomenon, like why would the ice ages be nearly periodic? And so what they did is they looked at all the little things that possibly could affect the amount of sunlight hitting the Earth, variability on the right time scale. And what they found is that there is an effect that occurs on the right time scale, which is the variation of the eccentricity of the Earth's orbit. So as you know, the Earth's orbit around the sun isn't quite circular, it's an ellipse. And the eccentricity of that ellipse is affected by the presence of the other planets, mostly Jupiter. Jupiter's the biggest one. And so that eccentricity of that ellipse does vary, and the period is very close to 100,000 years. And they said, well, that's interesting. Maybe that's the cause. Oh, and also the sign is correct that, if you look at the variation of eccentricity, you get a little bit more, you get a little bit more sun hitting the Earth, because on average, it's a little closer, you figure out what the total flux is. And you actually do get a very small change in the amount of sunlight hitting the Earth with that variability on that time scale. But if you then estimate how big the effect is, it's quite small, and it's like an order of magnitude too small to explain the difference in temperature between the ice age and the not ice age. So what they thought about, what Benzi et al. Did, is said, well, there's a small perturbation, but maybe there's a mechanism that enhances the response of the Earth's climate to a very small perturbation. And that's what stochastic resonance is. All right, it's the idea that there is other variability in the system, and that other variability enables the system to respond more to a deterministic drive than would otherwise be possible. So Benzi et al. Then boiled it all down to a very simple picture. All right, and this picture is going to be the picture I'm going to use during the whole talk. So I'm going to go through it in a fair amount of detail, and I'll say that if it's not clear, you should stop me. Okay, when I get to the end, I'll stop, and if it's not clear, please say in the Q&A and what your question is, because it's really important for the whole talk. Okay, so again, these are the references, but here we go. And so this is sort of the picture where this is supposed to be an ice age, and this is sort of not an ice age. When Wisconsin, where I was for many, many years, was, in the ice sheet, and now it's not. So now we're not in an ice age. But the idea is that there's sort of two states that the Earth can be in. One is ice age, and the other one is not ice age. And then this variation of the amount of light hitting from the eccentricity change. Then the idea is that really, like, when there's less radiation hitting the Earth, then it's a little more likely to be in the ice age. But then, when the eccentricity is such that there's more light hitting the Earth, then you're more likely to be hot. But the idea is if you're in one state, the odds of getting over to the other state, look very unlikely just based on the size of that perturbation. But the idea then is actually there's a source of noise, right? In the ice age issue, there was, the variability of the Earth's climate. And the idea is that there are fluctuations anyway. And if you're slightly more likely to be, I'd say let's start over here. If you're slightly more likely to be cold, and then you lower, then you lower the, this well that's the ice age, then you make it, you can't make it on your own steam. So here you are, there's this little perturbation, but if you don't have enough noise, you just stay in whatever well you're in. But if you have enough temperature, it can kick you over the barrier. All right. Now, a lot of work went into, is there a barrier and is this a good picture? And in the classical system, that's actually quite a complicated question. But in the quantum system, I'm going to tell you about, it's absolutely well established what's going on, and that's not a problem. So I'm not going to get into that at all. I'm just going to say, let's assume the picture works. And in the case that I tell you about, it's going to work. Okay. So just think about this double well. And again, if the temperature is really small, I stay in whatever well I'm in, no matter what happened to the Earth's perihelion. All right. On the other hand, if your noise is huge, it doesn't care, right? It just sort of, the sky could be on either side. It just wanders about. And the noise pushes the particles between the two wells much faster than the drive. And so you don't see anything to do with the drive. Okay, but it turns out there's a temperature, there's an amount of noise where as this double well is going back and forth, the noise gets you over the top, but it's synchronized with the drive. Okay, and here you can see you get a large response to a small drive, and it is response to the drive. You see what I mean? It's not just random noise, but the drive is kicking you over the barrier. Okay, so that's the origin of stochastic resonance. And I have to say that it is not totally accepted. It's totally controversial still, whether that is the explanation of the Earth's ice ages. But in the meantime, stochastic resonance has been shown to occur in a variety of classical complex systems. And one very interesting example was actually the response of neurons, that, you get a very small stimulus, but again, then noise in the system causes the neurons to fire even when the stimulus is very small. And so that's very well established and, interesting from a biological perspective. And then in the meantime, it's been used in other, again, other cases where you want to get a big response to a small drive and you want some amplification mechanism. Okay, so that's what stochastic resonance is. And about 30 years ago, again, through some sort of, accidental story, I became interested in the question of whether stochastic resonance, the phenomenon, can occur in quantum systems as well as classical systems. And at the beginning, you think that this is not a very good idea. Okay, and that the reason for that is that everything I've told you about stochastic resonance was this idea that I have my particle, I have my system, and it's like, well, if the noise is little, it's stuck, and if the noise is big, you can go over the barrier. Okay, and then you find an amount of noise that just gets you over the barrier. Well, in a quantum system, there's quantum tunneling, and quantum tunneling can happen even at zero temperature. So you can have, absolutely zero temperature, your system can tunnel. And so sort of the picture I showed you just, doesn't apply. Okay, but what we noticed was that's true, that's true if the system's completely symmetric. But if you have an asymmetric system, then what can happen is it's true that one of the rates is independent of temperature and stays finite at zero temperature, but there's the uphill rate. The other rate is still temperature dependent. So it's quantum tunneling, totally quantum dynamics, but because you have an asymmetric system, you do have a temperature dependence that's very strong at low temperatures, but just for one of the rates. So that led to the question of, well, okay, we have a system that can go back and forth, and in one direction, noise really affects the rate. And so can you get stochastic resonance in that situation? And so it turns out the answer is yes. And these pictures are, just to try to make you believe me when I tell you the answer is yes, of why it's true. And basically the fundamental piece of intuition is, well, there's like one rate that's really slow. And so if the temperature is 0, you just get stuck in one of the wells. And then there's no response because you're never in the, if you were in the higher energy state, you would decay, but you never get there because you're always stuck in the low energy state. And so then the question becomes, can I get out of that low energy state? Can I get out of, this guy on the left? Okay. And so again, this epsilon is the asymmetry. And so then again, what we're thinking about is the rate, the decay rate is independent of temperature, but the excitation rate grows exponentially with the ratio of epsilon divided by KT. So KT is a noise. If KT is really small, then you don't have enough energy to get up to the upper well no matter what, and you can modulate it a little bit. That's the drive. If you modulate it with the drive, it still can't make it, and so nothing happens. Right? If the temperature is really high, and now when we say high, we're not talking about actually going over the barrier. You're still tunneling in both directions, so it is a quantum system. But the point is, the rates become essentially equal because you always have energy to make it up to the upper well. Okay, so so the rate out of the upper state is again independent of temperature, and the rate into the state is essentially independent of temperature because it's just as big. So it just goes back and forth randomly, and you can modulate epsilon a little bit and it doesn't care. However, right in the middle, when epsilon is of order KT, medium temperature, then again, you make a small change in this distance, this energy epsilon, the difference in energy between the two states, and it has a big effect on whether you can make it from the lower state to the upper state. So, so basically what happens is that you see very similar phenomenology as in the classical case. Okay, so I do want to say what happened was in the 1990s, Rifa and I wrote this paper saying, oh, well, this concept that has been shown to be applicable to a lot of classical systems also is applicable to classical systems. It's also applicable to quantum systems, but at that time, no experiments were done. And essentially the reason is that in order to do these experiments, the easiest way to do it is either you modulate, when you do these things, the way to do it is to modulate the temperature. And when you're at really, really low temperatures, it's actually very hard to modulate the temperature. Very briefly, what happens is that basically the lower you get, the harder it is to cool more. Okay, and so if you want to be in the quantum regime, you're at low temperature, and so then you heat it up, but then it takes a long time to cool down. So to have a fast modulation of the temperature is actually really difficult experimentally. Okay, so there it was. We wrote it. We thought it was interesting. We said we should be able to see this, but it wasn't possible at the time to really do it in a nice, clean way. But in the meantime, there's just been tremendous progress in nanotechnology. And in particular, there's been tremendous progress in a lot of areas of nanotechnology. But the one I'm going to talk about is one where people have been able to do studies of individual atoms using scanning tunneling microscopy. Okay, and this the Nobel Prize was for the original technique was given in the early 80s, but over the last 10 years, people have been able to generalize this technique in order to study magnetism of individual atoms. So basically, we're looking at the spins of individual atoms you know, using scanning tunneling microscope. So again, so what this picture is that this is a substrate. It's a very smooth substrate. In this particular experiment, it's a magnesium oxide. It turns out the choice of substrate is very important in order to get the experiment to work, but not important for anything I'm going to tell you about. Okay, and then you have this tip, and the trick of this tip, and what distinguishes it from earlier experiments that were not studying magnets, is that this tip is magnetized, right? So just think of this as a giant magnet, but it is like, it goes down and the tip is actually of the size of one atom, okay? And then through that tip, electrons tunnel, and the green things are iron atoms, and they have a spin. And if you apply a given voltage to the tip, then the amount of current that flows through the spin depends on the orientation of that spin. Okay, so the tip sets a magnetization direction, and you get different amounts of current if the iron atom spin is parallel or anti-parallel to the tip. Okay, and then again, this is where the choice of the substrate comes in. For that particular substrate, you actually can watch that atom, that spin flip, okay? Because this is conductance. So when we say conductance, is again, you apply a voltage through the tip, and then there's a current, and the conductance is just the current divided by the voltage. And then when the spin flips, the conductance changes, okay? And so what they actually measure is the conductance, and you can see that, sometimes the conduction has one value and then it flips, it goes to the other. And again, one of the tricks of the experiment is to get the flips on a time scale where you can resolve them in the experiment. But it turns out this magnesium oxide substrate does that. And so basically you can just read off which direction your spin is pointing by looking at the conductance through the tip. Okay, so that's point number one of this experiment. Point number two, which was sort of the new thing that had never been noticed before, was that when they did this, and then what they did is they just said, oh, if the conductance is bigger than a threshold, which is this gray line, it's in one state, and if the conductance is less than that threshold, it's in the other state. Then you have what's the probability you're in that excited state? The thing that they noticed is that probability depended on the voltage applied at the tip. Okay, and so what this is just, the fraction of the time you're in the excited state. And if you increase this voltage between the tip and the substrate, you see you can really change the probability that, of going up. You're changing the transition rates of going up. So now all of a sudden you had a really nice way of modulating that asymmetry. Okay, so actually it turns out it's it's an effective temperature. It's actually noise that you're adding to the system, but there's this very, very well-defined, easy to modulate way of changing these rates. Okay, so that was the trick. So that led them to do this experiment. Okay, and so here's the idea. So basically, again, what you've got is this tip. You apply this voltage. Oh, the tip is magnetized. It stays magnetized the whole time. You apply this voltage. You measure the current. You modulate the voltage, and that does two things. One of which is it changes the transition rate, so it modulates the probability of making these transitions. And then the other thing is that you're still applying the voltage, and so you can measure the conductance all through this process. Okay, so okay, so that's what this is doing. So again, there's drive, you drive the voltage, but the voltage changes the transitions, and yet you measure just the current, and you can drive and measure with the same STM tip. Okay, so the first thing that you do when you do this, you just say, well, let's just look at what these transition rates are. Now, because they're voltage dependent, they now depend on time. So every time you go through a drive period, the relaxation, again, is that goes from the upper state to the lower state. It relaxes down to the lower state. And you see it's essentially constant. And then, but then the excitation rate varies by quite a lot. It varies by about a factor of 3. Okay. And this is the voltage. This line here is you apply the voltage, and then that voltage causes the rates to vary in this way. Okay. Then what we can do is see what happens to the dynamics of this quantum spin. And so well, I'm going to try to argue to you it does stochastic resonance, okay, but here because we have this direct measurement, we can see, sort of what some of the key physics is. And one thing which that Sebastian and his group realized that we hadn't really focused on when we did our calculations is that the way to think about this is that the transitions are synchronizing to the drive. The noise causes synchronization. So I want to explain that to you. Okay, so this is just what the rates are doing. And again, all you're supposed to really notice is that the up transitions depend on where you are in the drive period a lot. And we're going to actually approximate, for purposes of this discussion, the relaxation of this being constant. So just think about the excitation. Okay, so what's going to synchronize is the up transitions, all right? So what happens is, well, I'm going to show you the synchronized one, all right? So here you see, when we put on the drive, that transition gets much faster. And you see here it is, it went up, all right? It went up once that period. It went up once this period. It skipped this one, it's not perfect, but it goes up once this period, once that period, once here, and once here. So you see out of what, 1, 2, 3, 4, 5, 6, 7, 8, 7 of them had one up transition in the period. Okay. So now let me compare to the fast and the slow. Okay. So here what we did is everything is the same except the drive is really slow. Okay, here it's 2 kilohertz. If this one it's 0.2 kilohertz. And you see this one, when the transition rate goes fast, there are a bunch of transitions, right? And now there are a bunch. Every time there are a bunch. So you don't have one transition per period, and so you're not synchronized to the drive. The other case that I'm showing you here is that you're modulating really fast. So your drive is much faster than 2 kilohertz. And here you see, look, I go up here, but I don't go up here. This one goes down, going down doesn't count. This one goes up, but you see I've already at 1, 2, 3, 4, 5. It's like, it's 4 periods later, okay? And then here it's a couple periods later. This one's the next one, but then you see it's not the next one, okay? So what, and again, this was Sebastian and his group realized that this is the way to think about like what's happening is that the transitions are synchronizing to the drive, okay? All right, so that's actually what they're gonna plot, and here you can see the strength of the effect. All right, so again, this is now they took what I showed you before was like the real data of the conductance, but now what we're going to do is just show you like the thresholding that they used, and so it just looks very square, but that's just because the data has been analyzed. And what we're going to plot is a histogram of the time between successive up transitions. See, here it went up and the next one is here, okay? And then you take this time and then you put in this histogram, right? And so if there's no drive, you get a completely smooth curve. But then if you get a drive, you get a big peak here. And then what they call the synchronization efficiency is just the area under that peak. And just basically it says like, what's the time to the next one and what's the probability it's like within a quarter period of being like synchronized with the drive. And the here, I think I have the next one. Oh, I'll go back to show you that. Here's the next one. The synchronization efficiency, just for this case, which is not a completely modulated drive, but nonetheless, the synchronization efficiency is like pretty high. It's like 35%. Again in this case. Now, I do want to, since I'm a theorist and I did the theory, I do want to point out that the theory we did actually is the black line. All right. And let me tell you about the black line just for a moment. The point is that the black line is what we do to get it is we say, let's take those transition rates the rate of going up at that given voltage and the rate of going down at that given voltage. And let's assume that there's a very fast, the system forgets where it came from pretty fast. So that if for the aficionados, it's called a Markovian approximation, that you make a transition and then after a very short time, you forgot when you got there, right? And if you assume that Markovian dynamics, it turns out you can solve for time-dependent transition rates exactly. And that's what we did. And we took the rates as measured, using them as input, then you can calculate all these dynamical curves. And again, no additional parameters. You see that you can, it describes the data really well. Okay, so that's telling you that the idea that the spin flips, but then it doesn't remember when it got there. It doesn't remember when it flipped. But there is some probability of it leaving that doesn't depend on when it arrived. Okay, and that seems to be very well borne out in this experiment. Okay, so again, the key is that the synchronization frequency, the synchronization efficiency has this, really quite substantial peak, and in that sense, it is a resonance, that there is, a frequency that's picked out that's set by these rates, and the system responds more at that frequency. So let's see. Actually, what I have here are sorry about this. I'm looking at the chat. Oh, here we go. Oh no, this is old chat. Okay, so let me ask if there are questions there, because what I have next are I can tell you a little bit about the theory and how the theory is done. But let me just ask, was that clear? Is there anything you want me to discuss in more detail? Otherwise, I'll tell you a little bit about how we calculate these kinds of things. So I'm just going to stop for a moment, and if you have a question, please put it in the chat right now.
There's a question here.
But I am not. Yeah, go ahead. Just ask it. Yes.
So I just want to ask, in the theoretical explanation first, we were kind of comparing drive that changes the heights of the wells, and then you have temperature that controls the sort of stochastic rate of jumping between them. But then it seems sort of in the experiment, what you're driving with is more actually controlling the stochastic rate, more like a temperature. Then because you're not changing the sort of chemical potential of the two spins, right? You're just so
that's exactly right.
Because the only thing that matters is U over KBT. So
yes, that's exactly right. I was just going to say that the only thing that matters is the ratio of every energy scale to KT.
I see.
So in our case, in our case, we worry about this asymmetry, but all units are measured in KT. So you can either change in energy or you can change the temperature, and it's equivalent.
Perfect.
So that's a great
Thanks.
question.
Great.
Yeah. So you have 5 minutes more.
Oh, okay. Well, then I'll tell you 5 minutes of theory, and if I go on too long, I can talk all day on theory, but I will stop. Okay. Okay, but again, I can also talk a little bit about this, why it's okay to think about the noise or the energy scales. Okay, so the theory, as we worked out, was based on previous work by McNamara and Wiesenfeld. And again, I told you just in words what the assumptions were, but again, the idea is that there are two states. Again, in our case, up and down. If it was the ice ages, it would be hot and cold. But here you can think of spin up and spin down. And then there are two rates. And if you're in this state, there's some probability you'll get out. And if you're in this state, there's some probability that you'll go the other way. Okay. And the idea is that the system is in one state or the other. And again, so you can write a simple differential equation that says, if I'm in state n minus, there's some probability I'll leave, and if I'm in state n plus, there's some probability I'll come in, and I just go between the two, and the things have to add up to 1. Okay, so then you can you can solve this differential equation, all right? And now being more specific about the difference between the classical and the quantum, classically, the rates are e to the minus, are proportional to a Boltzmann factor. So there's an exponential of, u is this height plus epsilon of t. That's the modulation, is epsilon of t divided by kt. Okay, but here you see, everything depends on energy divided by kt. All right. Okay, and so then in this classical case, then again, what I showed you the pictures that, if u is really high or t is very low, you're stuck. If u is really, if u is really big, then you just go back and forth. You don't even notice that the barrier's there. But it's at this intermediate value of temperature, which is of order u, where you get the maximum response. Okay, so now so now in the quantum case, I just did the classical case, and now here's the quantum case. Here again, one of the rates, this W minus, is now essentially independent of temperature, right? And the rate that is modulated is the up rate. But again, this one's independent of temperature, and the ratio is e to the minus epsilon over kt. So once again, I can either modulate epsilon, the energy difference, or I can modulate kt, and it's the same, because everything comes in through those rates, and the rates depend only on the ratio. So that's just a longer answer to the question that you understood. You actually understood that this was going to be the answer. So that's why it doesn't, that when we do the theory, we don't care how the rate is modulated, whether we do it through energy or do it through temperature. We just use the rate, the measured rate that you get, and then that's the basis of the theory. Okay, and then basically, again, I'm not going to go through all the math, but I am going to show you one formula just so that you know that they're long and complicated. But you can derive closed form expressions for basically anything. Okay, so these rates, the synchronization probability is the thing I'm actually going to show you. And when you work out the theory, it turns out that, we never use the form of the rate, so they work for any rates. And so they work for the classical case, but they also work for this case of quantum tunneling. Okay, so this equation I wrote down. Okay, and again, the fact that the system is somewhere, this just says that NE plus NG, E is excited and G is ground, but they add up to 1. So you can, it's just a simple differential equation with one variable that you can write the solution to. And this is actually the formula for that curve that we use to get the synchronization probability. And everything can be interpreted. There's just a probability that you make your first transition. Then in order to make your down transition, it happens at a given time. And when it happens, it didn't make it before it did. Then it made it at that moment. Now it's up. Okay, then you went up at this time. Now we go down, and then we want the second transition to be a fixed time from the first one. And so this is like, I didn't make the transition before then, and I make it at that time. Okay, and it's that kind of thing. Actually, all the formulas are pretty interpretable. And but the fact that it's all, it was fun. Okay, it was fun because everything worked out in such a way that, again, I have explicit expressions for the power spectrum, for the synchronization probabilities. It's all, yeah. And so when we compare, there's no fudge parameter, right? It's just, you give us rates, we tell you what we expect. And one thing that's interesting about that as a result is just that what it is then it means that you can test your assumption, right? Because there's no approximation involved in the theory. So one thing that we're exploring is saying, well, look, let's look in a region where we can't resolve the individual transitions. You can still you can still measure in the range that you can. You can also measure in DC. And again, the theory makes very precise predictions of what you should see. And if you don't see it, that's actually a sign that the system is remembering the past, and it's the first signs of quantum coherence in the tunneling. So that's something that we're exploring and trying to find. Okay, so I did want to just say, again, I wanted to say that in addition to seeing this phenomenon that, we had predicted all these years ago. So that was fun. But the theoretical approach, I think, will give us a new window into being able to probe the high frequency dynamics of these kinds of systems. Because again, if the dynamics are Markovian, we get exact results. And so failure of the theory is actually probing the assumptions of Markovian dynamics. The other thing which is very useful is that sort of being able to, modulate the response, which is sort of why we think neurons explain stochastic resonance, is something that you may want to do in these kinds of experiments. And the theory, again, it should be able to enable the experimentalists to optimize the synchronization when they want things to be synchronized. Again, I already told you about this. This, I think, is the most interesting thing, is a window onto the high frequency dynamics that would not otherwise be available. And then finally, and one thing the experimentalists are working, quite hard on is you can do more complicated systems, coupled spins, for instance, is something, and to see whether you can really control where you end up by modulating the dynamics appropriately. And I believe that, oh yes, here's the summary, just to have you as to have it during the questions, is again, hopefully you learned about stochastic resonance if you haven't before, and the fact that it seems to appear in this really surprisingly broad range of application areas, and the generalization to quantum systems, I think, has some promise for being able to manipulate in this nanotechnological domain, and so we're hoping to extend that more in the future. And I want to thank you.
Thank you very much, Prof. Thank you. So let's thank Professor Susan for the talk. Let's thank her. We have time for one question before Professor Marcello Damonte comes.
Thank you for a great talk. Thanks, Susan.
Hey, it's just, sorry, I have one more question. Thanks so much for this talk. When I think about resonance, there's sort of two things. One of them is that I align something on the same frequency, and the other is I get a bigger amplitude response than I would if I were not on resonance. And that's sort of what I saw with the Earth temperature, that it both lined up, and we also got a bigger response than you would expect from just this, from the small production, from this eccentricity.
Yeah. We want that one. Yeah.
In experiment, I see that it lines up at the same frequency, but I guess you don't really get a bigger response, right? Because I mean, it's still just, so is it the exact?
I'm not sure they did this. Okay, let me actually go back. I'm not sure I showed this. No,
sorry, maybe
I sort of want to get a different talk for you. Okay, so there's a little bit under the rug. I tried to hide it. I didn't hide it too much, but so one of the things is that if you look as a function of noise, then you absolutely get a peak as a function of noise, of noise amplitude, because I'll just talk my way through it. Okay, that again, like if you're stuck on one side, there's like no response, and then you raise the temperature and you get response, so you get more signal. And then the fact that it goes down again at high temperature, I'd have to dig through my slides. I'd have to dig through another talk, but there is a peak as a function of noise. But what happens as a function of frequency, if you just look at signal to noise, it does not have a maximum. Okay, and so so it's actually one of the areas of contention is stochastic resonance or resonance. So when Sebastian and this group, like they said, but if we think of it as a synchronization, then it's clear that there is something as a function of frequency. So it's sort of weird, right? Because signal to noise does the classic thing. You get a maximum response, okay, but as a function of the noise, okay. And the synchronization is you get something as a function of time, but it actually does what you say, that You know, again, it depends on exactly how your rates are modulated. But you certainly can have situations where, you know, unmodulated rates are all faster, and so therefore you get more transitions, right?
Yeah, I see. Okay. Thanks.
Yeah, so it's a little more complicated because it is stochastic, I guess is the short answer. Okay.
Yep.
Okay, thank you very much, Professor.
Okay, great. Yeah, again, thank you for the opportunity. I really appreciate it.
Thank you very much.